In this video, I'm going to be going into the idea of covalent bonding. And what bonding really is a shared pair of electrons. And molecules are the smallest part of a covalent compound, so a compound which contains covalent bonds. Molecules are the smallest part of a covalent compound which can take part in chemical reactions. Now, molecules consist of two or more atoms together through covalent bonds. And so you can imagine if two atoms were to share electrons, they would become molecule. They would become a molecule. So let's say two agents like fluorine. So if fluorine, which has I would just draw the electrons in the outer shell. Fluorine has Fluorine has 7 electrons in its outer shell. So if fluorine, let me just draw these electrons on there. So 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. So this is, and as you can see, both of these fluorine molecules have an unshared. It has an unshared electron here, and this one has an unshared electron. And what these two atoms can do is share their electrons. So form a covalent bond by allowing the atom to share the electron that it can share the electron that the other atom has. So this fluorine would bond together, and what I'm going to do is I'll represent the atoms of this fluorine with actually I won't do that. I won't use notation simply because it's just they're both the same atom. But if fluorine was to bond to the fluorine, so and I will just switch to purple. But if fluorine was to bond to the fluorine, what we have in the middle is a shared, those two electrons be shared there. So and then it would have, both of them would have, you could imagine they would have like 8 electrons, though they're sharing one of them from them. Now, why atoms do this, the reason why atoms form covalent bonds is because when bonds are made, energy is released. When made, energy is released, and with less energy in these structures, they're more stable. And so what atoms tend to do is they'll form as many bonds as they can so that they increase the stability. And as you can see, it's got lone pairs. So you may be wondering, why doesn't it use those lone pairs to form some more bonds? Well, if fluorine, well, not fluorine, but any atoms tend to be a bit like reverse business people. So what these fluorines tend to do is, if you imagine energy is like currency or money, what the fluorine doesn't think, but what it just I'm trying to put this into a kind of perspective. But what the atom is basically doing is it's thinking that, okay, if I form this bond, the energy I use to separate these into single atoms before I form that bond, will I use more energy forming the bond than I use separate the electrons? And if more energy is used to separate the electrons, as in if it takes in more energy to separate the electrons than it loses from forming the bond, then it probably just won't do it, because it's going to gain more energy overall by doing that. And so they like to form bonds when it's favorable, so when they're going to lose. And this concept is going to come in handy going to looking at really covalent compounds with loads of surrounding atoms. Okay, so this here is a single covalent bond. So it's a single shared pair of electrons, this bond right here. And this isn't the only thing that can happen. If we take an oxygen atom, for example, So an oxygen atom. I'm only going to draw one just to represent what it looks like in terms of its outer shell electrons. So oxygen. So oxygen has 8 protons and has 8 electrons as well. So it's going to have 8 minus 2, which is 6 electrons outer shell. So what oxygen has is 1, 2, 3, 4, that's 5 and 6. And so here is two electrons which are unpaired. If you draw a configuration, you'll see why they're unpaired. What this oxygen likes to do is form a bond, share this electron and share that electron, because it would be more stable, because energy would be released when it forms those bonds. And so what we have in the air that we breathe in is oxygen molecules, and oxygen molecules have double bonds between them. So no one's double bonds. And so if we were to imagine an oxygen bonding to this, I'll actually draw out 2 more oxygen. So if we had 2 oxygen molecules bonding, what they would do is, rather than having like maybe bonding to one atom, one element here and one element here, which it does do in H2O, but when it's bonding to oxygen, we would call this a diatomic molecule. What it does is it forms a double covalent bond. So it would have a and so what would happen is we'd have a shared pair of electrons and a shared pair of electrons. So we'd have 2 pairs of electrons in this part of the structure. No, I did not just do yeah, let me just, I drew some extra electrons, extra mystery appearing electrons by accident. Yeah, it only has 2 lone pairs of electrons after it does this. I drew like 3 lone pairs per oxygen after by accident. So it only has 2 lone pairs. So yeah, this is what it would look like after, as you can see, a double bond. So this is one covalent bond. If I draw a line here to represent that bond, it's from one covalent bond here and one covalent bond here. And we could also write this like this. So we'd have an O and a double bond and an O, represent the double covalent bond which we have here. And so this oxygen bonded in a molecular form like this is more stable than an oxygen like this with the 2 alone single unpaired electrons. And so that's why it forms molecules like this. And so the only thing that can happen, if we consider nitrogen, what nitrogen likes to do when it's in the form of a molecule, so bonded to other nitrogen, what nitrogen to do is form a triple bond. And nitrogen has, I think, 7. Yeah, it's got 7 in total. So if we were to draw that structure, nitrogen, N, yeah. If we were to draw the electrons on the outer shell of nitrogen, it's got 2 on the inner outer shell, so we'd have 7 minus 2, which is 5. So 1, 2, 3, 4, 5. And looking at this, right, we can see that nitrogen has blessed 3 unpaired electrons. Let me draw out the electron configuration of nitrogen. It has a pair electron pair here, so let me just draw this out. 1s2. I'm not sure if it has two lone pairs or just so 1s2, 2s2, so that's 4, and then it has 2p3. Oh right, that makes sense. So it has 5 on here. Oh, wait, what? So this is the outer shell. Alright, it's got outer shell. That makes sense. Yeah. So nitrogen has let me just get rid of these. Yeah, nitrogen has 2 electrons in its outer shell, and it's got 3 single electrons as you can see, the 2s squared is this part here, and the 2p3 is this 1, 2. Because as you remember from that from one of my previous videos about electron configurations, what the electrons like to do is, first of all, it will fill one orbital at one orbital only after the other ones have been partially filled, so before pairing up. So we've only done this so far, so that's why these aren't paired up. And anyway, so it likes to do to make this a much more stable arrangement is it will form bonds with this, and this. If you imagine a nitrogen bonded to another nitrogen, is then in that case form a triple bond. So it would form N bonded to an N. Yeah, this isn't a circle, but anyway, to an N. What? My tablet seems to be acting. Okay, so N triple to an N, and what we'd have here is a 1 bond, 2 bonds, and 3 bonds. Okay, let me draw a huge electron here, since it doesn't seem to. This is one pair. So this nitrogen, this belongs to this and this belongs to this nitrogen, and then this one belongs to nitrogen. This one belongs to that nitrogen, and this one belongs to that nitrogen. So we've got a pair here, a pair, and a pair here, and then so these nitrogens would each have a lone pair of electrons on there. Yeah, this is much more stable. This is a much more stable arrangement than just having those unpaired electrons like this, because energy is released when bonds are made. And apart from this, there are some exceptions. So sometimes sometimes what happens is, I've seen it explained. I don't know why they make such emphasis on that rule. Like sometimes it can get quite confusing. But you might have seen textbooks or something that there's the octet rule. You've probably seen this before. For the most part, you can use the octet rule to think, okay, how many bonds is this going to form? But sometimes it doesn't really help us to really understand why what is happening. It really doesn't. Sometimes it doesn't fully explain why this happens. Like, okay, we could use it and say, okay, for this case, we can use it and say, fluorine has 8 electrons, like a noble gas in its outer shell. Yay! But for some molecules, they don't actually go with this octet. Like if you imagine boron trifluoride, for example, and if we look at the group that boron is in group 3, and it has 3 electrons in its outer shell, and none of those electrons are paired. So what I'm going to do is the electron configuration of boron trifluoride and BF. Yeah. Okay. So boron has the electron of 1s squared, 2s squared, 2s squared, and then 2p1. And so as you can see here, what we have is that boron has the electron configuration 1, 2s2, 2p1, and so it's got 3 electrons in the outer shell. And so really all it can do maximum is form 3 bonds with other atoms, and that's what it does in boron trifluoride. What it's like when it's done this is like this, B, and then we have the, so that I'll draw this with a slight green. F, and then F here. So this is what boron trifluoride would look like, and if I was to draw the electron here, I'll draw the boron's electrons light red, and I'll draw the fluorine's electrons in yellow. So these are boron's electrons. It's only got 3, bear that in mind, outer shell. On its outer shell, it's only got 3. And so this is what it would look like in terms of the. Now, problem with the octet rule when it comes to this is that it explains fully what's gone on here. What's gone on here is boron has gone for the most energetically stable form, which is when it's quite as many bonds as possible in an energetically favorable way. Because when these bonds, energy is lost from the fluorine atoms and energy is lost from the boron atom, and so all of these atoms collectively are more stable. This is why this forms. The way it forms, I'm not going to explain it in this video. Yeah, I don't want to make this video to be too long. But I will make a video explaining just that why how it does this, because it usually has a lone pair. And another fuel which I want us to take a look at in this video is SF6, and SF6 is sulfur hexafluoride, and this is another rep which isn't which doesn't follow the tech rule. And there's a reason for this, but I won't explain it in this video. But sulfur, what the structure looks like for sulfur hexafluoride is this. So alpha in light. This looks like a yellowy green, so light green. Olive, I'll draw it in olive. I guess this is olive. So sulfur and the fluorine, so I'll draw that in green. And we've got 6 fluorine molecules actually bonded to this sulfur. So 1, 2, 3, 4, 5, 6. I don't know why my tablet is lagging. I will check it after this video. So we've got 6 there. 1, 2, 3, 4. We've got 6 here, and I'll draw the sulfur's molecules atoms. I'll draw sulfur's electrons in yellow. So 1, 2, 3, 4, 5, 6. And I'll draw the electrons for the different fluorines. The fluorines in a bluish green. So we've got the electrons of fluorine here. And so this is the fluoride. And what it's done is it's used its d orbitals. Oh, let me draw the F's on here. It's used d orbitals to expand the amount of atoms that it can bond to. And so usually sulfur forms a compound which has bonded to only 3 atoms, 3 different atoms. But in this case, what it is done is it's managed to bond to 6 atoms. And the way it involves d orbitals, but I won't go into the full in this video. But this is one of those things. Is another case where the octet rule is not obeyed, but it's much more stable in the structure. So yeah. Anyway, so sort of stuff about covalent bonding and molecules, and I hope so. Yeah.